See, when it comes to chemical bonding, we need to check between two atoms what are the interactions we'll have. Usually, between two atoms, we will have nucleus nucleus repulsion, nucleus electron attraction, nucleus, the second nucleus, and the first nucleus, first atom's attraction, or electron electron repulsion. If out of these interactions, if attractive force is been dominating, then this will result in formation of a chemical bond. This will result in the formation of a chemical bond. You can see between two atoms, if the distance is very large, there is no bonding, there is no interaction, so the potential energy is almost zero. As it approaches close by, the potential energy starts decreasing, which means it will go in a negative scale. And as it forms a bond, it will reach to a minimum potential energy. And this minimum potential value is also known as the bond enthalpy of that atom. Okay. So between these atoms, how much is the bond form? That is the bond enthalpy. If you try to decrease the distance further, in that case, the repulsive forces will dominate and potential energy suddenly raises into the positive scale. Okay, this is a typical scenario in a bond formation. There are mainly three types of bonds we will notice. One is ionic, covalent, and coordinate. Metallic is another kind of a covalent bond. Then between the molecules, we will have van der Waal and hydrogen bonding. So these are the types of bonds we generally see. Okay. According to Coastal-Lewis theory, an atom will always try to reach the 8 electronic system in the valence shell. And this ability to reach the valence shells to get 8 electrons brings the stability. And we can represent the valence electrons before and after the formation of the bond. Before the formation of the bond, these are the number of electrons present with each and every atom. For example, boron. Boron will have 3 electrons. Carbon will have 4 electrons to interact. Well, it may have configuration as 2s2 and 2p2. But while interacting with other atom, it will interact all its 4 electrons like this. So you can see these are known as the valencies. Hydrogen has 1, helium 2, lithium 1, 2, 3, 4, 3, 2, 1, 0. These are the respective valencies. Okay. The valencies are also known as the maximum number of bonds they can form. Got it? So with the given number of atoms. So it can make 4 simple bonds. Here this can make 3 simple bonds, 2 simple bonds, 1 simple bond. Okay. If there is a complete transfer of electrons, like from this element, an electron has been lost and this element is taking away electron, then you get ions. And the ionic interaction is what we call it as the ionic bond. Okay. Notice ionic bond is an electrostatic attraction between oppositely charged ions. That is, if you have one electron completely transferred, this will become Na plus Cl minus. This will have 2,8 and 2,8,8, and you can see the octet is completed in the valence shell. Similarly, MgCl2, you can get Mg2 plus Cl minus and Cl minus interacting with it, make it as an ionic bond. Covalent bond is all about sharing of electrons. Okay, if you have this single electron on hydrogens, if they share, that will become a bond pair. And bond pair can always be written as a single line for covalent bonds. Okay, and that is the molecular form of H2. H2 is stable due to formation of duplet configuration. O2, on the other hand, shares one electron from here, one from here, one from here, and one from here. So it makes two bonds here. So you can notice that there are two bonds. In the valence shell, it has 8 electrons. This oxygen also has 8 electrons. So there are two bonded pairs, and these electrons are called non-bonded pairs or lone pairs. So there are a total of two bond pairs and total of four lone pairs present in this molecule. N2, on the other hand, forms triple bond So three bond pairs and two lone pairs are present in it. Let us understand this term formal charge. A hypothetical or a real charge assigned to every element in the molecule is called as formal charge. See, it is the difference between valence electrons and number of electrons assigned during the bond formation. Formal charge is how many valence electrons we have minus how many lone pair electrons plus shared pair electrons present with us. Okay, clear? So we will draw some structures and see how to calculate the formal charge. O3, for example, O3 sharing should be such a way, see the total valence electrons are 18. Each oxygen is contributing 6 electrons. Okay, which means I need to complete the octet of each and every oxygen here. So for that, I need to take two bond pairs here and one pair of electrons from this oxygen. So that completes the octet of this one, that completes the octet of this one. So this is structurally, this is how it looks like. There are two bond pairs in between and one bond pair here. So total number of lone pairs are 6, bond pairs are 3. Okay. This oxygen has two lone pairs. This oxygen has three lone pairs. The center oxygen has one lone pair. Now notice formal charge on the first oxygen. Valence shell electrons are 6 minus bonded pair electrons are 4, right? That by 2 plus number of lone pair electrons are 4. So that makes the formal charge as 0. For second oxygen, valence shell electrons are 6. Bonded lone pair electrons are 2. Bonded pair electrons are 6. These are 6 divided by 2. So that gives the formal charge as 1. Formal charge of oxygen 3, if you notice for this oxygen, there are 6 valence electrons, 6 lone pair electrons, and 2 bond pair electrons divided by 2. So that makes it minus 1. So this gets plus 1 charge, this gets minus 1 charge, this has 0 charge. So that is how you need to represent the structure of O3. So I got one more example of carbon dioxide. Carbon plus 2 oxygens total valence electrons are 16. This is the best possible structure we can imagine where octet is completed for all three. Now lone pair electrons are 4, bond pair electrons are 4 for the overall structure. Now if I take this as oxygen 1, you will see it is 6 valence electrons minus 4 lone pair electrons. You can, these 4 are lone pair electrons. These 4 are bond pair electrons by 2. So that makes it 0. For carbon, if you notice, you can see for carbon formal charge, 4 bond valence electrons, 0 lone pair electrons, 8 bonded pair electrons by 2. So that makes it 0. So the formal charge is 0 in all of them. Okay. Generally, to write a structure, we will always try to figure out whichever is the least electronegative element and try to make that as a central atom. Assign all the side atoms and make sure it is symmetrically distributed. Then complete the octet on all the atoms by arranging the electrons and finally evaluate the formal charge. That is how we generally write a structure, Lewis structure. Coordinate covalent bond is sharing of electrons only by one species, while the other species is not sharing, but it is involved in using that electrons. For example, between A and B, B is sharing the electrons with A. A is not sharing a single electron. So both these electron as a pair came from B only. So such cases are called coordinate covalent bond. Okay. Coordinate covalent bond, we should always represent an arrow in the direction of electrons where it has been given. Or if this is the direction in which electrons were given, the giver will become positive, the taker or the acceptor will become negative charged. So the same arrow can be represented as negative, positive with a covalent bond. We can use it like a covalent bond and write it as negative and positive. Okay. So in case of O3 also, here if you notice this was plus 1 and minus 1. And plus 1 and minus 1 can be converted into this arrow. Okay. So the bond pair remains the same. These are 2 plus 1, 3 bond pairs and 6 lone pairs. Okay. Check out NH4 plus. Nitrogen will complete its octet by making four single covalent bonds. Okay. But if you notice the formal charge on nitrogen, 5 valence electrons, 0 lone pair electrons, 8 bonded pair by 2, that makes it plus 1 charge. So nitrogen has plus 1 charge on it. Okay. And formal charge on all hydrogens are 0. So how do we write down? This is how we write down. Towards H plus. Towards H plus we have. Okay. With formal charge, if you have to write, how do we write down that? We will write as a covalent bond here with plus charge. This is with, writing this as the covalent bond. Clear? Now, if you want to write the dative bond, then make this as negative. Clear? And make this as positive. So negative positive will become 0 and this will remain H plus. Got it? Notice this. If you have BF3, which will act like a Lewis acid, when NH3 with the lone pair present on it will donate electrons to it by dative bonding. This is how we write it down. Okay, if you write it in a covalent bond format, write it as plus and minus. So this will become the structure, bond line structure. Okay, next. Writing all the structures, SO3 for example, right? We will get to complete the octet. When sulfur has been completing octet, oxygen is completing octet, and these oxygens are also completing octet, then you will get this kind of form. Okay, so you'll get 1, 2, 3, 4, 5, 6, and here we'll have 8, here we'll have 8. Okay, so sulfur will get plus 2 as the formal charge. These two oxygens will get minus 1, this will get 0. Okay, so it is as if this plus 2 and minus 1 can be written as plus 1 minus 1, as one dative bond here and one dative bond here. So SO3 can exist in this particular form with two dative bonds. Okay. Same way PO4 3 minus, same way SO4 2 minus and NO3 minus, we can do that. Okay. Mathematical finding of SUR. SUR is, here, for example, if you notice total number of valence electrons, we write it as V. Okay. Number of electrons actually required to make the noble gas configuration is R. Total shared pair electrons are S and number of unshared pair electrons are U. So now you notice that S represent, right, number of shared pair electrons, which is equal to number of electrons required to achieve valence electron octet completion minus V valence electrons, and U is V minus S. Okay. For example, if you take H2SO4, V value is 32. That is total valence electrons are 32. Okay. To reach the octet, then how much do we require? 44. Because hydrogen requires 2, sulfur requires 8, oxygen requires 8. So that's how it is 44. The difference of those two is 12, which is the shared pair of electrons. And 32 minus 12, which is 20, which is the unshared pair of electrons. So bond pairs are 6, lone pairs are 10. So this makes bond pairs, this makes lone pairs. So this is the hint we need to take and then draw the structure. So total maximum number of bond pairs I can put is 6. So you can see 1, 2, 3, 4, 5, 6. 6 bond pairs I keep. And how many lone pairs I can keep? 20, so that the octet is complete. So you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the octet is complete in all of them. So once you write this structure, then you can represent them in dative bonds. I hope all of you understood mathematical technique of writing Lewis structure. Okay. Same logic goes for H3PO4. What are the limitations of octet? See, if there is an incomplete octet, okay, BF3, BeCl2, AlF3, AlCl3, BH3, in all of these cases, they have either 4 electrons or 6 electrons in the valence shell. Okay. Next, dimerization or polymerization that takes place here. For example, if you take BH3, 2 moles of BH3 will become B2H6. AlCl3, 2 moles will become Al2Cl6. Okay. You can notice now boron is trying to complete its octet, right, by making a bridged bond here. So two electrons here, two electrons here, and these two will make a banana bond and make a cloud of two electrons. These two electrons will make a cloud of two electrons. So in a way, boron is getting support of 8 electrons. So that's how octet is getting completed. Same way, beryllium chloride, right? If it goes n times, here also you will notice that it will have, octet completed by making bridged bonds. Okay. So usually octet incomplete molecules are not very stable. They'll try to undergo dimerization or polymerization. Expanded octet. See, in incomplete octet elements are also known as hypovalent. These are also called as hypovalent cases. And while these are called as hypervalent, hypervalent means expanded octet. Okay. If you notice PCl5 has bond electrons of 10, which is greater than 8, which means these are hypervalent bonds. Okay. So involvement of d orbitals are also been observed. Therefore, they will expand the octet. See, NF5, NCl5, OF6, OF4, FCl7, FCl5, these does not exist. Why do they do not exist? Because they do not have any d orbital. In fact, all the second period elements, carbon, nitrogen, oxygen, fluorine, they cannot expand their octet. Clear? Next, odd electron cases. NO, NO2, ClO2, ClO3, these are all those cases. ClO3, BrO3, clear? These are all those cases where there is a single electron present on them, extra electron or incomplete electron. So you can see NO, you will have this one electron present on nitrogen, which is not making octet completed on nitrogen. Similarly, if you notice NO2, it could this electron can appear on oxygen and nitrogen like this and make a resonance by but that octet will not be completed for all of them. ClO2 no octet completed. Okay. So here also these odd electron cases they have a chance to undergo dimerization. NO will dimerize to N2O2, NO2 will dimerize to N2O4, ClO2 will dimerize to Cl2O4 and so on. Okay. Clear everybody? Next. Noble gas expanded octet. So all the noble gas compounds will always have an expanded octet only. Only krypton and xenon forms the compounds. Kryptons KrF2, xenon F2, xenon F4, xenon F6, xenon O3, xenon O4, and lot of compounds of xenon are present. And all of these are formed by expanding their octet. Okay. There is some justification of octet for PCl5 and some other cases. Like in case of PCl5, right? Just on heating PCl5, it will give you PCl3 plus Cl2. Okay. So this was justified by Sidgwick's rule. Sidgwick's singlet bond rule. What he says that, see, there are regular simple covalent bonds, like these three are simple covalent bonds. But then there are phosphorus and chlorine, if you notice, correct? Here, up and down bonds, you notice. Here only chlorine is sharing, sorry, phosphorus is sharing, chlorine is not sharing electron. By which the octet is completed for phosphorus, octet is completed for chlorine. This chlorine also octet is completed. Okay. But this is not a bond of two electrons. So that's why it is called singlet bond. So if I place that singlet bond, because it is not a stronger bond, its bond length will be longer and bond energy will be weaker. So this bond energy will be stronger compared to that of this bond energy. That is what we are trying to represent. Okay, so singlet bonds are weaker than regular covalent bonds. This was a justification given, but this is not true. So according to Sidgwick's rule, you will see SF4, SF6, ICL5, ICL7, where expanded octet is there, we all can show them as an octet completed using singlet bonds. SF4, I can make two covalent bonds and two singlet bonds. Got it? So we can see that two singlet and two normal bonds we have. Next, electronegativity series. We know that whenever we have, fluorine, oxygen, nitrogen, chlorine, these are all the composition of electronegativity. The other day also we learned. If electronegativity is greater than, difference is greater than 1.7, ionic bond favors or the character favors. Character develops. Here also character develops. Covalent character is more. We say if electronegativity is less than 1.7, we'll say covalent character is dominating. Or if it is greater than 1.7, we say ionic character is dominant. Okay. SF6 also has four singlet and two normal bonds. Okay, these are all the representations. Next, what is the concept of covalency? Number of valential electrons to form covalent bonds are called covalency. For example, in PCl5, all five electrons are involved. So to form covalent bond. So therefore, we call the covalency of phosphorus in this case is 5. The maximum covalency of phosphorus in PCl5 is 5, right? If you take PCl3, only 3 electrons are involved. So the covalency of phosphorus in this case is only 3. PCl3. PCl3 is only 3. Okay. Check out the covalency in the following nitrogen molecules. N2, 3 bonds are involved. So 3. NO, 2 bonds are involved. NH3, 3 bonds involved. NH4 plus, 4 bonds involved. HNO3, 4 bonds. Now notice carefully, this is the important one. HNO3. Nitrogen is making a dative bond which will count it as only one bond. So 1, 2, 3, 4. Maximum it can form 4 only because it cannot expand octet. So here NCl3 will have 3 covalent bonds. Okay. So maximum covalency of all these elements, right? Nitrogen, oxygen, boron, beryllium, fluorine, carbon, carbon also. These all will have maximum valency of 4. Covalency, maximum covalency of 4. Next. Resonance is a delocalization of pi electrons. We learned it already. So O3, which is structurally written in this format, can also be written in this format. The same minus can be put on this side and we can make these two bonds forming. Clear? Okay. So these two are the canonical structures and this is how the hybrid looks like. Right? Bond characteristics, if you notice, the bond length between O1 and O2, if I write it here, this one, O1 and O2 in the first structure, L2 will be greater than that of L1. So here, this length is greater than that of this length. But bond energy of this one will be greater than that of this one. Okay. Bond order is 2 and 1 here. Same logic for 1 and 2 here. But actual structure, L1 is same as L2, E1 is same as E2. And bond order is 1.5. And that is what is showcased in hybrid structure. Generally, average bond order will be equal to total number of bonds divided by number of structures. And the average charge is equal to total charge divided by number of structures. For example, if you notice CO3 2 minus, CO3 2 minus have three canonical structures and this is the hybrid for carbonate. Average charge will be equal to how much charge we have? 2 minus charge. So 2 minus charge divided by 3 structures makes it minus 2 by 3. And average bond order will be, you can see between two atoms here, 2 bonds, 1 bond and 1 bond. Total 4 bonds are there. So 4 bonds divided by 3 structures. So that makes it average bond order. Okay. So I was expecting you can practice this one. Write the bond order as well as the average charge on each element for this canonical structure for these molecules. Write the structure, write the canonical structures and practice. Next, when it comes to ionic bonds is purely electrostatic. Positive and negative charge must be present. Okay. Usually, for ionic bond formation, we should understand what is Born-Haber cycle. Okay. Na sodium plus half of Cl2 giving NaCl. This is thermodynamical formation equation. Okay. So for formation equation, the delta H of formation of NaCl need to be found. So Na converting into solid converting into gas is a sublimation energy, and gas converting into an ion is an ionization energy. This is already in gas converting into atom. We will have dissociation energy, and from there we have electron affinity for introducing an extra electron. So when these positive negative charges together will combine, it will form NaCl, and the energy released is called lattice energy. So addition of all of these will give you delta H of formation. So sublimation is positive, ionization and dissociation is positive. Electron gain enthalpy and lattice energy is negative energy or exothermic energy. So you can notice lattice energy, amount of energy released when two gaseous ions from far away distance approaches to form 1 mole of a ionic solid crystal. That is called as lattice energy. For ionic bond to form, we should have low ionization energy of the positive ions, high electron affinity of the negative ions, delta N. That is, electron into difference should be always greater than 1.7. Valence electrons of the metal should be 1, 2, or 3, while the valence electrons of the non-metal should be 5, 6, or 7. Okay? And high lattice energy is always expected. Lattice energy is the force of attraction between the two ions here. So Q1, Q2 by R square is the force of attraction here. Correct? So lattice energy will be force of attraction multiplied by the distance, bond distance here. Okay. So you can notice that. So lattice energy is directly proportional to charge and inversely proportional to bond distance. So this is how the lattice energy depends on Q1, Q2 or Q plus Q minus by R plus R minus. Now notice this. If you compare LIF, LICL, LIBR, LII, lattice energy, what would happen? You can see this one fluorine is smaller in size. Charge wise, everything is same. Everybody has plus one, minus one, plus one, minus one, and so on. But fluorine is smaller compared to chlorine, bromine, and iodine. So that's why smaller value of radius will dominate. So lattice energy will be in this order. NaCl, MgO, AlN, and TiC. So here, charge is always going to dominate. Plus 1, minus 1, plus 2, minus 2, plus 3, minus 3, and plus 4, minus 4. So lattice energy will be more for plus 4 and minus 4 case. Lattice energy, if you notice this here, this is plus 1, minus 1, plus 2, minus 1, plus 3, minus 1. Again, the charge will be dominant factor. So Al F3 will have more amount of lattice energy. And same logic applies to all these examples. Just check it out once, everybody. So this is about lattice energy. Next. What are the main properties of ionic compound? They are crystalline in nature. They'll form various structures, FCC, BCC, HCP, and so on. High boiling point, melting point, and density. They are non-directional in nature. They do not have any direction. Electrical conducting only in the molten or aqueous state. Otherwise, it is insulator. Okay. Next, solubility of ionic compound. It is highly soluble in polar solvents. Solvent with high dielectric constant dissolves ionic compounds better than the others. Okay, so you can see solubility. If a molecule AB, which is ionic compound, is added to infinite water, if it converts completely into A plus and B minus, then the energy released is called as delta H of solution, released or absorbed. The energy required to break this solid into gaseous ions, that is called as lattice energy. And this is a positive lattice energy. Okay, energy is required here. Gaseous ion converting into aqueous ion is called hydration energy. So this hydration plus this hydrogen will give us total hydration energy. So delta H naught of the solution will be equal to delta H naught of U plus delta H naught of hydration. If hydration energy dominates, then the salt will get completely dissolved. Lattice energy dominant, it is sparingly soluble. If both of them are equal, that is a saturated solution. Okay. Notice hydration energy. Hydration energy depends mainly on the ions. Like if it is for a positive ion, then it's charge divided by radius. For negative ion, it's charge divided by radius. Okay. So this is the total hydration energy formula. This is the total lattice energy formula. Okay. So hydration energy depends mainly on the charge and size. You can see lithium in aqueous solution has a you know first Li plus gaseous state has the smallest size. So that smallest size will have strong amount of attraction with water molecules. So therefore, this will have highest hydration energy. So after hydration, Li plus aqueous is formed, and the size of this Li plus aqueous will be the highest of all. Okay. Check out hydration energy in all of these cases. Everything is in gaseous state, by the way. All of them are in gaseous state. So in gaseous state, you can notice which one will have more hydration. First factor should be given chance to charge more than size. Charge is a dominant factor. If charge is same, then only you should compare size. Finished everybody? See, generally, when it comes to solubility of salts, okay, down the group, right, the solubility of the salt is, why whether it decreases or increases, it depends upon two factors. If hydration energy is more, solubility is more. But if lattice energy is more, solubility is less. So these two factors are inversely proportional. Okay. Now let us see the first set. First set where lattice energy is decreasing, hydration energy is decreasing, but the hydration energy is decreasing much more faster than lattice energy. Then solubility will decrease. Okay. So notice this, when lattice energy decreases slowly, when lattice energy decreases slowly as compared to hydration energy, the solubility of salt decreases down the group. Okay. You can see large anions. These are all large anions here. These are all big anions. So when you have big size anions, the hydration energy decreases faster than the lattice energy. So what should happen to the solubility? Decreases. So it will decrease down the road. So that's why you will see Na2SO4, K2SO4, Rb2SO4, CH2SO4, solubility will decrease. Okay. Barium carbonate, down the group solubility is decreasing. Okay. Exceptionally, the exception is only for these three. HCO3 minus, CO3 2 minus. For group 1, solubility will increase down the group. For oxalate, only in group 2, solubility will increase down the group. These two are exceptions. Other than that, if you apply it for anything else, solubility will decrease down the group. Everybody understood what are exceptions and what are the other cases? Next, set B. In set B, lattice energy is decreasing faster than the hydration energy, therefore solubility will increase. So if lattice energy decrease faster, then the solubility will increase. This happens with the smaller ions like F minus, H minus, OH minus, O2 minus, Cl minus, Cn minus, and all of this. For example, if you take F minus, correct? Exceptionally, beryllium will have very, very high, high solubility because of high hydration value. Other than that, regular trend should be followed. That is, barium is greater than strontium, calcium, and magnesium. And beryllium oxalate are also same thing. If you notice the oxalate also, that will have exceptionally high solubility. So these two are exceptions that you need to know for a solubility. Okay. Alkali metal halide solubility for fluorides, this is how it is. CSRB, K plus, Na plus, Li plus. For bromides, it is, for chlorides, it is Li plus, Cs plus, Rb plus, Na plus, and K plus. Okay. For Br minus, this is how the solubility is. For I minus, Na plus, Li plus, K plus, Rb plus, and Cs plus. These are the solubility for alkali uh, halides, metal halides. Okay. Next, let us understand what are Fajans rules. See, the ability of ionic compounds to exhibit covalent character is called as Fajans rules. Basically, here the concept of polarization is introduced. Okay. There are two parts of polarization. One is polarizing power, the other one is polarizability. If I take two ionic compounds, if I take an ionic compound of two ions, Li plus and I minus, Li plus, the positive charge, has the ability to pull the electrons towards itself. So that's why it will distort the cloud of the negative ions. Okay. This ability to distort the cloud is called as PP, polarizing power, how much power lithium has to pull the electrons. Next one, polarizability. Polarizability is that it is the tendency of anion to push the electrons towards positive charge. So that what we will write it as PZ, polarizability. So PP is polarizing power, PZ is polarizability. Okay. See, if both the characters increases, covalent character increases. Polarizing power depends upon how much is the charge on cation and what is the size of the cation. Okay. Pz is directly proportional to charge of the anion and also directly proportional to size of the anion. Okay. So if you notice, polarizing power, Li plus will have more than Na plus, Nk plus, Rb plus, Cs plus based on size. Based on charge, Al plus 3 will have more than Mg2 plus, more than Na plus. Next, polarizability. Based on size, iodine is bigger, so that will have better polarizability. Based on charge, C4 minus is, more charge than N3 minus, O2 minus, and F minus. This is based on charge. Now notice these examples quickly. Covalent character, NaCl, MgCl2, AlCl3. Out of this, AlCl3 will have the highest polarizing power because aluminum is at plus 3 charge, magnesium is at plus 2 charge, sodium is at plus 1 charge. Next, BeCl2, MgCl2, CaCl2, and BaCl2. Again, beryllium is very small in size. All of them are plus 2, but it is the size which you are comparing. Beryllium is small in size, so very high polarizing power, so more covalent character. Next, lead with plus 4 and plus 2, obviously plus 4 will have more covalent character. Again, calcium, here it is with respect to the anions. Bigger the anion, more is the covalent character. Same is the logic with this next case. Copper, calcium, and zinc. If you notice, anything which has D10 completed will have very high polarizing power. So Zn2 plus will have high polarizing power, then copper 2 plus, then calcium 2 plus. Okay. Similarly, if you take CuCl and NaCl, Cu will have similar radius as that of Na plus, but this will have a pseudo octet completed or inert gas completed structure. So therefore, this will show covalent character. So this is also going to be covalent character. Next, AgF, AgCl, AgBr, and AgI. Okay. So AgI is the covalent. AgI will have the highest covalent character. Next, application of Fajans rule. If a compound sustains heat before the bond starts breaking, this is called thermally stable. And more ionic character, more is the thermal stability. See, for thermal stability cases, what you will notice, we'll check out two sets again. Set A is when you have a single atomic anion species. If you have only one anion, like N3 minus, O2 minus, H minus, Cl minus, F minus, C4 minus, these are all single atom anions. For these cases, thermal stability is directly proportional to lattice energy. So you can see down the group lattice energy decreases, so thermal stability decreases. Down the group lattice energy decreases for oxides, so thermal stability decreases, and so on for all the cases. I hope this set is clear, everybody. Set 2 is multi-atomic anion. Multi-atomic anion. So you can see these are all multi-atomic anions. Okay. In this case, if lattice energy decreases, right, then the thermal stability increases. It's in a exactly opposite way. LiClO3, NaClO3, KClO3, and ClClO3. Now you notice that polarizing power, if you notice, lithium would have greater than that of cesium. Okay. But covalent character, if you notice, would be more for LiClO3. Thermal stability will be exactly in the opposite lines. Okay. So if you have multi-atomic anion, see even OH is a multi-atomic anion. So don't see the size, always see multi-atomic. Okay. So OH is multi-atomic. So that will have lesser lattice in thermal stability as compared to barium hydroxide. Okay. And that logic applies to all the cases. In general, thermal stability is always proportional to melting point. So you will notice the melting point will be same as that of thermal stability. Special cases is that when it comes to group 1 and group 2, check it out. NaCl, KCl, RbCl, CaCl, and LiCl. This is same for chlorine and bromine. NaF, KF, LiF, and then RbF and CSF. This is for melting point of fluorides. For iodides, Ki, Nai, Rbi, CSI, and Lii. This will be for iodides. Okay. Oxides, MgO, CaO, BeO, SRO, and BaO. Fluoride, CaF2, MgF2, SrF2, BaF2, and BeF2. This will be the combination for melting point. Okay. Next, acidic character. If the polarizing power increases, acidic nature always increases. So if you compare these three, correct? Li2 has more polarizing power, so it has more acidic nature. Li2O compared to that of BO, this one, and N2O5. N2O5 will have high polarizing power, so therefore it is most acidic. Al2O3, MgO, and Na2O3 acidic character increases this way. Cl2O7, SO3, P2O5, SiO2 acidic character increases. Carbon dioxide and carbon monoxide, more polarizing power, more acidic. SO3, more polarizing power, more acidic compared to SO2, and all these examples. Okay. Typically, we are aware of the type of solvents. One is polar, the other one is non-polar. Non-polar are these kinds. Polar, we have two kinds, polar protic, polar aprotic. These are polar protic, these are polar aprotic. We have come across this before. Okay. Now notice solubility of salts. If it is polar protic solvent, AgF will dissolve very easily compared to AgCl, AgBr, and AgF. If it is polar aprotic solvent or a non-polar, the order is exactly reverse. Here, next. In covalent bonds, we have seen what are the conditions. Electronegativity difference should be less than 1.7. It should be between non-metal and non-metal. Valence electrons of electronegativity will prefer when you have +3, +4, higher oxidation states, higher valency of the elements. That will give covalent bonds more than ionic bonds. Okay. If the dipole moment is zero, we call it as polar covalent bond. If the dipole moment, sorry, non-zero, it is polar covalent bond. If it is zero, it is non-polar covalent bond. Okay. Number of shared electrons between the atoms. If there are two electrons, we write it as single bond. Four electrons, double bond. Six electrons, we write it as triple bond. There are two types of overlapping, sigma and pi overlapping. Along with that, we will go through the concept of back bonding, which is also an overlapping, and hybridized orbitals overlapping. Okay. See, physical state wise, they exist in gaseous, liquids, and solid forms. Van der Waal interactions are generally observed in these cases, right? Gaseous, these are the typical gases, these are typical liquids and solids here. Melting point and boiling point, generally covalent will have low melting point and boiling point, okay, due to van der Waal interactions. Graphite diamond will have exceptionally high melting point because of their covalent bonding itself. They do not have any van der Waal. The molecule itself is a giant molecule. So exceptionally high boiling point and melting point are observed. Except graphite, most of the covalent compounds are poor conductors of heat and electricity. Okay. HCl, they will show the electrical property in aqueous solution. Okay. Solubility wise, they are more soluble in non-polar solvents and they are less soluble in polar solvents. Okay. Or polar covalent compounds will dissolve in polar solvents. It is highly directional in nature. It will have a specific shape and geometry whenever there is a covalent bonds or covalent molecule is present. Okay. To explain the bonding, first we need to understand VSEPR theory, valence shell electron pair repulsion theory. See, this will give us the idea about the shape and geometry of the covalent molecule. For this, what are the conditions? Molecule must have greater than or equal to three atoms connected with each other, right? One should be designated as central atom, other are side atoms. Now, geometry is decided based on how many bonded pair electrons we have and how many lone pairs electrons do we have it. You see, bond pairs, lone pairs arrange in a space around the central atom to exhibit minimum amount of repulsions. So the whole purpose is to minimize the repulsions only. The whole purpose of VSEPR theory is to minimize the repulsions. Order of repulsion is like this. Lone pair, they are maximum repelled with each other, then lone pair, bond pair, then bond pair, bond pair. And total number of pairs around an atom will be bond pairs plus lone pairs. All double bonds, triple bonds are considered to be single bond only for our purpose. Arrangement of bond pairs and lone pairs together is called as geometry. Arrangement of bonded pairs only is called as shape. Okay. See, if you have electron pairs as two and there are no lone pairs here, so only two bond pairs are there. So one is a central atom, other two are side atoms. Then we can have two bond pairs. So the most convenient way to minimize the repulsion is to keep opposite to each other, makes it at 180 degrees angle. Okay. So AB2 is a linear shape and linear geometry. Okay, these are the examples: BCl2, BF2, BH2, CO2, ZnCl2, HgCl2, CS2, NO2 plus, and so on. Three pairs are there. Three bond pairs are only there. No lone pairs are present. In that case, this is how the shape maximum best shape possible is 120 degrees turn. So 120 degrees angle will make it as the geometry and shape as trigonal planar. BF3, BCl3, NCl3, SO3, NO3 minus CO3 2 minus BH3 and so on. These are all examples. Two bond pairs and one lone pair. You can see this is bent V shape or angular, and that is the shape is what we call it as trigonal planar. Okay, sorry, this is the geometry and this is the shape. This is the shape and this is the geometry of that molecule. So obviously lone pair, bond pair repulsions will be more. So here the bond angle is more, here the bond angle is less. These are the examples: O3, SO2, SnCl4, PbCl2, NO3 minus, and so on. So about AB4. AB4, bond pairs are 4, lone pairs are 0. So here you can notice that between these two, the bond angle is 109, 28 degrees. Shape and geometry are same. It will be tetrahedral in structure. These are all the examples which are tetrahedral in nature. Okay. So now you see there are three bond pairs, one lone pair, and AB3E is the shape. So this is the shape by which you will have. So the shape is pyramidal, and the geometry is tetrahedral. Okay. So you can see NH3, H3O plus, PCl5, CH3 minus. These are all the examples. Bond pair are two, lone pairs are two. Okay, just like in water. So in this case, these two angles, This is far greater than 109. This is also greater than 109, but the bond angle here is smaller. And in fact, for water, the bond angle is 104 degrees 5 minutes. For ammonia, it is 107 degrees. These two you have to remember. Okay. So these are few examples where you will notice it. Next, if electron pairs are 5, there are two things we need to understand, that there are equatorial bonds and axial bonds. Three equatorial bonds and two axial bonds we have. Okay. So you can see there are two types of bond angles here. This is one bond angle, which is between axial and equatorial, which is around 90 degrees. Then we have between equatorials, so that is 120 degrees. And there is one more angle, this one, which is axial and axial, which is 180 degrees. Okay. So there are 690 degrees angle, making it as maximum repulsions. So this will usually have maximum repulsions. So therefore, to avoid the repulsions, you will always try to place the more electronegative on the axial direction. So remember, this is called Bend's rule. That is, most electronegative elements prefer to stay in the axial bonds to minimize the bond repulsions. To minimize the bond repulsions, most electronegative should be on the axial direction. Check out these examples, everybody. PCl3F2. Where should I place fluorine? On the axial direction because it is more electronegative. PCl2F3. So first two I have to put it in axial. The remaining one I have to put it in equatorial. PCl3Br2. Again, 2 Cl here, 1 Cl here, and the rest of the 2 Brs here. PCl2Br3. So Cl will goes here, all Br will come here. PCH3 twice and CF3 twice. So CF3 will go here. One more CF3 is there, which is left here. And methyl should be always on equatorial direction. So these are few examples where you will have difference of compounds and they will have some Bend's rule to be applied there. Next, notice it. Bond pairs are 4, lone pairs are 1. In that case, we will have one lone pair and lone pair always need to be placed in equatorial position. And because of that, there will be some repulsion here and some repulsion here and it will convert it into a new shape here. This is called seesaw shape. The geometry is TBP only, trigonal bipyramidal only, but the shape now has changed to seesaw. Very important examples, everybody. Please remember these examples. SF4, TCl4, XeO2F2, PCl4 minus, and so on. Okay. Next. If the bond pairs are 3, lone pairs are 2, lone pairs has to be maintained on the equatorial position. So that will give repulsions on both sides. Make it as a bent shape here. Make it as a bent shape. So we can say this as, we will have bent T shape here. And geometry will be trigonal bipyramidal. The geometry will be trigonal bipyramidal. So ClF3, IF3, ICl3, and so on. This is all the trigonal bipyramidal shape. Okay. Clear on that, everybody? Next. Check out here. Bond pair are 2, lone pair are 3. Okay, so AB2, E3. So shape would be linear, correct? Because all the lone pairs will be placed on the equatorial position. Geometry is trigonal bipyramidal, but the shape is linear. Again, important examples. Notice I3 minus, ICl2 minus, XeF2, IBrCl minus, Br3 minus. These are all examples of, linear shape. If all the bond pairs are 6, there are no lone pairs, then it will form an octahedral geometry and same as the shape. Interesting part here is the bond length of axial direction and equatorial direction are same. So you will not distinguish anything about axial and equatorial. So no Bend's rule is applied here. Okay. So when you have AB6 kind, no Bend's rule should be applied. So all of these are the examples of compounds. And next, if you have one pair of lone pair, you can place it in anywhere, whether it is axial or equatorial. I will put it on axial direction to understand the geometry. If I put it in axial direction, it is a pyramid. It is a pyramid which is only one-sided. So it is called square pyramid, and geometry is octahedral only. Okay. Due to square pyramid, there will be repulsion here. So these angles will not remain 90. So the none of the angles will remain 90 in this case. Neither the equatorial angle, neither the equatorial axial angle remains 90. So BRFT has been a very, very strong and standard example. So wherever you see BRF5, I mean BRF5, CLF5, XEOF4, they all will have this type of geometry and shape. Square planar, square pyramidal is the structure. Again, this is a JE question. I told you this earlier. How many bonds FBRF are equal to 90 degrees? And answer is zero. Because of the bent shape, none of them remain 90 degrees. Next. Four bond pairs, two lone pairs, right? In this case, the shape is square pyramidal. Geometry is octahedral. So XeF4, SF4, 2 minus, these are all the cases. Okay. Here the bond angle is always 90 now. Between these two, 90, 90. Here this will be 180 and 180. EP7 now. Okay. Now you will notice that, okay, bond pair is 7, lone pair is 0, AB7. So shape and geometry is pentagonal bipyramidal. IF7 is pentagonal bipyramidal. Okay. Now in this case, interestingly, if you notice the AB bond length between axial and A versus bond length between equatorial and A. In this case, the equatorial bonds are longer, everybody. Unlike in trigonal bipyramidal, here it is exactly opposite. So Bend's rule is applicable here again. So what do you do? Most electronegative should be placed. Okay, most electronegative must be placed must be placed along equatorial direction now. Equatorial direction. And lone pairs must be placed along axial direction now. Lone pair must be placed along axial direction. Okay. So next, BF's bond pair is 6, lone pair is 1. In that case, the shape is distorted octahedral. Okay, best example is XCF6. Here the lone pair will keep popping over every face. There are 8 faces. Once it will come out from here, here, like this. Okay, but remember, because lone pair is not stagnant, it will still remain non-polar. Will still remain non-polar. Even though there is lone pair, it will remain non-polar. Everybody clear with these cases? Now check out valence bond theory. Okay. First postulates. Atomic orbitals of valence shell with unpaired electrons takes place in overlapping, which leads to the chemical bonding. And there are mainly two types of extent of overlapping. One is axially head-on or end-to-end, or lateral, sideways, or parallel. Okay. Axially or head-on means it is happening on the internuclear axis. On the internuclear axis, if the orbitals are overlapping like this, then that forms end-to-end overlapping or sigma bond. If the parallel overlapping is happening like this is a parallel orbitals and they are overlapping, right? And it is perpendicular to the internuclear axis, then that is called as pi bond. That is called as pi bond. Okay. Sigma bond. That will be the first bond between any two atoms. And the bond forms between S and S, Sp, Pp, Pd, and so on. Okay. Here, uh, orbitals are approaching each other, making an pi bond here, sigma bond here, which is SS overlapping. Okay. In case of F2, these two, Pz and Pz are overlapping, so that will give you sigma overlapping. Sp in HF we will have S and P overlapping on the internuclear axis. Sigma bond is forming. So that is sp overlapping. The extent of overlapping, that means best overlapping, is observed in pp bond compared to sp bond then ss bond. This is the extent of overlapping which you will notice. And notice in pi bonds here, in pi bonds formed only after a sigma bond perpendicular to the internuclear axis. Okay, pp, pd, dd, these are the bonds which are formed. Okay, just a minute. So just notice of how the structure of N2 looks like, everybody. Please check out the difference between sigma and pi bond. This is end to end, side to side. Okay, electron cloud along the internuclear axis. It is above the internuclear axis. This is a stronger bond, this is a weaker bond. It can independently exist. This will only exist after sigma bond. Hybridization concept is applied, hybridization concept is not applied. Shape and geometry is based on sigma bond. Okay, no contribution towards the shape. Sigma is localized electrons, pi bond is delocalized between two atoms. Okay, clear on that? Right. Now, just one more addition here because I forgot to add that line. I would suggest you make a note of this one because I am not given in the notes there. See, if you have to predict the nature of the bond, okay, what is the nature of bond? Here, given the type of overlapping. So if I give you orbital and if I give you internuclear axis is what, and you should be able to figure out what is the bond that is forming. This is a must do question. Okay. Suppose if there is an S and S overlapping happening, if you take any axis, the bond formation is always sigma. Okay. If it is S plus Px and X is the internuclear axis, then it is sigma. Okay. If it is S and Px and Y is the internuclear axis, Y or Z is the internuclear axis, then there is no bond. Then there is no bond formation. Okay. It is like this way, bonding with this way. Okay. Internuclear axis is this one. So then there is no bond here. Clear? Next, S and Px, okay, and then we have, sorry, uh, the other one, which is Px and Px, Px and Px, internuclear axis is X, then there is sigma bond, okay, Px and Px approaching here, clear, and Y or Z is the internuclear axis, then it is pi bond. Got it? And vice versa. You can keep writing it for any other cases also. Okay, other cases as in suppose if I add px plus py. Okay, any axis you have, there is no bond here. Okay, no bond in this case. Okay, and pz and pz. If you have something like y, then also it is pi bond. Okay, so next, if you have dxy plus px or along y-axis, then this is pi bond. Okay, dxy plus px along x-axis, no bond, and dxy plus pz along x-axis, no bond. dxy plus dxy, okay, along z axis, okay, then dxy and dxy along z axis. This is called delta bond. This is the special bond. It is called as delta. Sorry, not sigma. Delta bond. Delta bond. Okay. So delta bond would be something of this sort. Everybody, if this is z axis, okay, and this is x axis, and this is y axis, and this is x axis, and this is y axis, like this. Okay. Then orbitals present here, this one, okay, this one here, and like this one, and here, this way, this way, this way, and this way. In this case, the overlapping goes like this. Okay, if the overlapping is between these two, between these two, between these two and these two. This way, if the overlapping is happened, that is called delta bond. This is z-axis. This is dxy and dxy. Got it? This is called delta bond. Okay. Next. So I hope this bond is clear, everybody. Okay. Now bond strength also. Another thing is bond strength. Bond strength. First for sigma bonds. Okay. Which bond is stronger? Please note this order and mug up. Okay. First 1s have the strongest bond. Then 1s and 2p. 1s and 2s. Then 2p and 2p. Then 2s and 2p, then 2s and 2s, then 3p and 3p, then 3s and 3p, then 3s and 3s, and so on. Okay. So for nth shell, generally for nth shell, pp sigma bond is always greater than sp sigma bond is always greater than ss sigma bond. Okay. Keep that in mind. Next, bond strength of pi bonds. If you notice bond strength of pi bonds, 2p will have more bond strength compared to 2p3d compared to 2p3p compared to 3p3d compared to 3p and 3p and so on. 3p and 3p and so on. Clear? This is the bond strength which you will notice. Please make sure that you are aware of these bonds, how they are formed. Everyone, sir, can you explain dxy along x? Okay. See, along x, if you take this as x-axis, if you take this as x-axis, okay. Now we will have y-axis like this. We will have z-axis like this. Okay. Where will be dxy lying, beta? Dxy means, okay, this is xy plane, this is x plane, and this is y plane, correct? This is that xy plane here. On this xy plane only it will be lying, so which means it will be like this, and here and here, right? This is how the orbital will be. This is about dxy. Where is px exactly? Px is in this direction. Px is in this direction, like this. This is px. Clear? So do you think we will have any bonding between these two? No bonding. Clear? dxy and px. Okay, so no bonding. Clear? So can you send a photo of this page in the group? Okay, sure, I'll send you the image of this group, so just please check it out once. Okay, this is dxy and this is px. Then, like, concept of hybridization, how it is evolved, I think that background we will not go through it. Okay, we will mainly emphasize on understanding what is atomic orbitals, what are hybridized orbitals, what is their difference, and then how many different types of hybridizations we will have. Got it? Clear? I think this I will take it in the class after your break time. Clear? One second.